An introduction to the mole. After listening to this screencast, you'll understand whether all atoms all have the same mass or not, and why that's very important. How big this number, Avogadro's number, is, and why on earth they chose that weird number, which is not an easy thing to explain briefly. And finally, if you're going a little bit deeper, you'll think about the relationship between the mole, which is the title of this unit, and stoichiometry, which is the fancy word that relates to this unit as well. This is Screencast 9.1. The mole. Let us begin by considering a simple molecule of water, H2O, which is bonded as shown here. The thing about water, and the thing about atoms in general, is that they're not all the same size, nor are they the same mass. Here's a real representation of a water molecule, taking into account the fact that the oxygen atom is much more massive than the hydrogen atom. In fact, it's 16 times more massive than a hydrogen atom, and you can use these average atomic masses anytime on the periodic table to get an idea of the relative masses of elements. If they were all the same size, life would be easy, 2 grams of hydrogen, 1 gram of oxygen, which give you 3 grams of product, nothing would be wasted. But if you did that, you'd have a totally insufficient amount of oxygen because it's so heavy, based on the fact that it weighs more. Okay, therefore, a gram of hydrogen atoms, right there, its average atomic mass, is defined as a mole of hydrogen atoms, and a mole is defined as a big number, 6 times 10 to the 23rd. How did they come up with that weird number? They decided to standardize on carbon-12. They calculated that 12 grams of carbon-12 had exactly 6.02 times 10 to the 23rd hydrogen atoms, and they defined that as a mole. That's where that number came from. Therefore, 16 grams of oxygen is also a mole of oxygen atoms, and therefore it's 6 times 10 to the 23rd oxygen atoms. Weighs 16 times more. So the mole is the SI unit for amount. It's that really big number, 6 times 10 to the 23. And let's apply it to make some water. We better balance this equation out first, and by now I hope you're pretty good at balancing these things. And this literally says, well, this literally shown, here's our 2 molecules of hydrogen, 1, 2. Here's our 1 molecule of oxygen, way heavier, way bigger. And there they are combining to form your 2 molecules of HOH, 2 molecules of water. That helps explain the stoichiometry. And so as written, this says that 2 moles of hydrogen molecules combine with 2 moles of oxygen molecules to make 1 mole, 2 moles of water. What I'd like you to think about is how many grams are involved in this synthesis. If you did it as shown, 2 moles should weigh exactly 4 grams. 1 mole should weigh a whopping 32 grams since it's diatomic, and it should give you 36 grams, and you can confirm that because number 1, 4 plus 32 is 36, but also 2 times 18 is 36. So the mole is very quickly giving us a nice, useful chemical recipe. You may want to write the gram amounts down below, even though it's not part of the screencast. We finish by defining this term stoichiometry. This comes from the Latin stoichion and metron. Stoichion means element, metron means to measure. Stoichiometry is all about element measuring. This is Screencast 9.1.